tried to condense this into a 10-minute presentation. So a number of things I'll be referring to back to the paper itself. All right, so my presentation is on a novel multi-precision floating point multiplier architecture using MANTISSA similarity investigation. And the purpose is for path delay reduction. So the structure of the presentation would be the introduction, contribution of the work in this paper, the design methodology, implementation, then we did some verification and validation testing, and then discussion and conclusions based on the research. So the arithmetic and logic units are very important components of processors. They perform various operations such as division, addition, multiplication, cubing, and so on. But of all these operations, the multiplication operation is the most elementary and most frequently used in ALUs, right? Now, based on Evan and Seidel 2000, it indicates that the floating point multiplication operations account for approximately 37% of floating point operations in application, especially benchmark applications, right? And generally, multiplication consumes a significant amount of time compared to any other operation that was previously mentioned, all right? Now, of the floating point multiplication, the MANTISSA multiplication component is the component that utilizes the most, it's most type consumed basically, right? So one of the focuses of this paper was to find approaches that would have resulted in the path delay reduction in this respect. So just to recap on the IEEE 754 standard for floating point standards, basically they have single precision, double precision, quadruple, and octuple precision. All of these have bits assigned to the sign exponent MANTISSA, and they also have the various biases. The difference is generally, the main difference is the dynamic range of numbers that could be represented using these floating point, these precision modes basically. All right, so as we move from single precision to octuple precision, we actually could represent much more numbers. Dynamic range of numbers increases significantly, right? So based on the literature review, which I referred to in the paper, we did a number of extensive review, and what I've realized is that the systems that existed, they have generally long path delays. The hardware utilization is generally high. The throughput is generally low, and the diversity in terms of precision modes also is not extensive. And none of them have actually looked at past multiplication operations as a means of affecting present or future multiplication operations, which is a major contribution of this paper. So the thing about it is that the contribution in terms of MSI, MANTISSA similarity investigation, it is supposed to be a system that is interfaced to the MANTISSA calculator. And MANTISSA calculator is basically that component that more or less computes the resulting MANTISSA. When you multiply two numbers together, float point numbers together, the MANTISSA calculator actually computes the MANTISSA component, right? And that component actually accounts, as I indicated previously, for a significant portion of the path delay when you actually do floating point multiplication. So the MSI unit is supposed to be interfaced to the MANTISSA calculator, and it should actually avoid the overall multiplier investing significant amount of time in computing the product of numbers that would have been computed in the past, right? They also has the memory storage element inside of the MSI unit was prepared to be self-ordering. So it means that when we enter new data, it actually will reorder itself in such a way that there could be quicker retrieval of data. So the concept design would have been that, you have the sign generator, the bias exponent calculator, the MANTISSA calculator at the bottom here. Then we'll interface the MSI unit to the MANTISSA calculator, which would result in the significant reduction in path delay, the rounding units, adjustment units, and then the data accumulation. So that's the concept design. So a couple of things to note before we go into the actual data path design for the system was that the MANTISSA batches. Now, what we were first thing to do, we actually found redundancies in the input batches, right? So if there were redundancies there, it doesn't make sense actually repeating the multiplication operation over and over if we have similar batches of data. So we would actually find the redundancies, compute the product, and then share the MANTISSA product and actually share that amongst the result amongst for the actual overall result of all the batches, basically. So we avoid the system performing duplicate search comparisons because for every batch we actually have to do a comparison in the MSI unit to determine whether that system was actually those inputs were actually multiplied in the past. So we actually avoiding duplicate search processes. Also, we avoid storing duplicates for future reference, future multiplication operations. And also the contents of the RAM block basically are ordered for quicker retrieval. And also the estimates of the product MANTISSA for input batches based on the past multiplication, we would to actually make the system a bit more effective. We have two parameters we focus on. They call a similarity code and also similar products. So basically, if there is any match when we do the comparison, the similarity investigation, we find a match, we'll actually indicate that on the similarity code, and also the similar product would be included as part of the data going forward. So this is the data path design. As you can see, this is the overall system. I actually tried to crunch it into one diagram where you could actually see all the words and so on. As seen before, it looks very similar to the concept design, but just there's more detail. They have the sign decoder, the novel multi-precision bias exponent calculator, the MANTISSA calculator, which is the novel multi-precision binary novel multi-precision binary multiplier system, right? And then we have the MANTISSA similarity investigator. Altogether, this creates the complete novel multi-precision floating point multiplier system. Now, it was implemented using the VHL IEEE 1076.3 and also information from Perry 1998, which is a very good text. Both the behavioral and structural approaches used, we used a foundation to roof approach, which you all would actually also know as from ground up, bottom to top approach, basically. While the design would have, of course, been from top to bottom. At the point of creation of this system, Xilinx 14.2 ISE environment was utilized. Now, in the testing phase, we actually had to use post-place and route static timing reports from the Xilinx ISE to actually retrieve a lot of the information for results. Now, this produced a number of path delays. What we chose was the worst case scenario, right? I didn't choose the best case, I would choose the worst case, so the maximum path delay was what was extracted. And that actually would consist of 3 parameters: gate delays, which would be signal delays due to actual logic gate transitions; wire delays, which also known as routing delays associated with signal propagation to lines, and also there is clock skew, right? So what I did also is that this system is capable of actually producing multiple multiple batches of product outputs, basically. So I could actually place multiple input batches, multiplicand and multiplier batches, and I could actually get the resulting output for all of them. So for single precision, I could actually multiply 8 batches at the same time, double precision 4, quadruple 2, and octuple 1. So what I did is for multiple platforms from Spartan 3 to the Vertex 6 at the time, and I actually extracted the maximum path delays with MSI and without MSI for those platforms. What I realized is now with MSI, the system behaves similarly if there's an input of 0 or 1 in any of the input batches, basically. So if the multiplier has 0 or 1, how the system is designed is that it would more or less avoid the extensive multiplication operation and just use we prepare a result for those scenarios. So MSI behaves similarly, and without MSI, the system actually has to go through the entire extensive multiplication operation, and that value I would have chosen obtained from the post place and route static timing report. I use the worst case scenarios. So as you can see with MSI, the path delays actually have been significantly reduced for all the platforms generally, right? So let's look at, for instance, over here for the Spartan 3, this is without MSI, it's 8.163 nanoseconds for 8 batches to be produced. And with MSI, it actually had been reduced to 4.841 nanoseconds. And that's the trend throughout. Now, I compared these values with actual systems from existing, we actually explored in the literature review. And they actually had outperformed those systems, those existing systems. The path delays for my system, for instance, this is a single comparison with my system and existing single precision systems. So, for instance, number 6, done on the XCV 300E Xilinx Vertex E platform, 37.55 nanoseconds. The hardware utilization is 2.967 slices. If we compare that with the Vertex E platform, right? We have a Vertex E. I didn't include it over here, but basically comparing them with let's say the Spartan 3, 2.29.72, and the Spartan 3 with MSI 4.841 nanoseconds, and this is 8 batches produced compared to 1 batch produced here by this this researcher, right? I did that for also the double precision, existing double precision point multiplier systems, which it outperformed the existing, and also for the quadruple, we found a couple of quadruple precision floating point multiplier systems. The same thing there. Now, at the time of research, there were no existing available octuple precision floating point multiplier systems. So that was not included in this presentation. But from that, there's a number of things, notable items. Now, the MSI attached to the front end of the MANTISSA calculator it resulted in a reduction in the path delay of the system in all precision modes when compared to the system without MANTISSA similarity investigation. Now, one thing is that this is at the expense of hardware utilization of the system. This system utilized a bit more hardware on all the platforms than existing systems, especially because of the existence of MSI, which required a significant, there's a significant memory requirement. Now, one other thing is that after a certain amount of multiplication operations, which I calculated to be about 68,345, the system begins to experience diminishing returns, because for every multiplication operation, something had to be stored about that operation for future reference. So after a certain amount of multiplication operations, we realized that the bulk of the path delay is spent in the search operation, and therefore it starts to impact the overall path delay. So after that amount of multiplication operations, I realized that the system tends to spend the share amount, the bulk of time, the path delay, in searching for compared to just the multiplication operation alone. The application of MSI could be applied to other systems. The floating point division is a key component that could benefit from MSI. Of course, the same parameters, the same expectations, we expect the same thing in terms of the diminishing returns after a certain amount of division operations, right? And well, all these, I expect all these to benefit computer arithmetic, especially other components such as the bias exponent computation and so on. They can be used to further reduce path delays. So there's many opportunities, things that we could do going forward to further reduce the path delay of the floating point multiplication operation. But a key thing now would be seeing if we could actually reduce the hardware utilization now. So find key ways to actually optimize the system in terms of hardware utilization, and that's a key thing going forward.